Atomic spectroscopy makes use of the absorption and emission of UV visible light by atoms and monoatomic ions. The electrons in atoms have different energy levels. So the lowest energy level would be the ground state. Then there are different orbitals with higher energy levels. Electrons can absorb energy to enter the orbitals with higher energy levels. When an atom has all electrons in their lowest energy levels, then it is said to be in the ground state. When the electrons occupy higher energy levels, then the atom is said to be in the excited state. Electrons that are in the higher energy levels of an atom in the excited state can also fall back down to the ground state. When electrons fall to lower energy levels, they would then emit radiation. So atomic spectroscopy makes use of this phenomenon to quantitatively analyze elements that are present in a sample. There are two types of atomic spectroscopy: atomic absorption spectroscopy and atomic emission spectroscopy. In this section, we'll be looking at atomic absorption spectroscopy first. Atomic absorption occurs when an atom in the ground state absorbs electromagnetic radiation of a specific wavelength and is converted to an excited state. In this diagram, we see an electron occupying the lowest available energy level. So this is an atom in the ground state, and by absorbing radiation of a specific wavelength, the electron can move up to a higher energy level, and this is called an excited state. So atomic absorption spectroscopy measures the amount of light that is absorbed by the sample at that specific wavelength. AAS is used to determine the concentration of metallic elements such as calcium, magnesium, iron, and sodium that's present in a sample. The Beer's law applies, which is the amount of light that is absorbed by the sample is proportional to the concentration of that sample. Therefore, we can construct calibration curves using solutions of known concentration. And from the calibration curve, if we know the absorbance of the sample, then we can determine its concentration. Different elements have different atomic absorption spectra, meaning that they absorb different wavelengths of light. In AAS, to test whether a sample contains a particular element, light from that particular element will be used. For example, if you want to find the amount of lead in your sample, then you will also need to use a lamp with lead as the radiation source. This is because when excited lead atoms fall back to the ground state, they would emit light of a characteristic wavelength. For example, 217 nanometers. And this is exactly the correct wavelength that needs to be absorbed by the lead in the sample. Let's take a look at what happens inside the atomic absorption spectrometer. The sample used is typically an aqueous solution. This sample is aspirated up into the flame. This causes the sample to evaporate and become atomized. Atomized means that the sample is now in the atomic state in the form of an atom vapor or a gas phase. The hollow cathode lamp is the light source and it emits light of that specific wavelength to be absorbed by the element. There are specific lamps for each element that you are testing for. So for example, if we are testing for lead, then we will use a lamp that is specific for lead. So the radiation passes into the flame and the atoms will absorb radiation of that specific wavelength. The light then exits through the slit and enters the monochromator. So the monochromator will select that specific wavelength at which the atoms absorb radiation. Then they would reach the detector where the intensity of the light would be measured. So to conduct an experiment, you would first put a blank as a sample and then use standard solutions with different concentrations. With that, a calibration curve can then be constructed. This calibration curve can then be used to measure the concentration of the sample. AAS has many applications in many different fields, but it is used mainly to analyze for metallic elements present in the sample. Among the applications listed here, the ones that will be most relevant to pharmaceutical or life sciences would be the clinical applications to test for metals, for example, in the urine or in the blood. For example, it is very common to test for sodium or potassium levels in the blood. In the pharmaceutical sector, AAS can be used as limit test for metal catalysts in final products. For environmental applications, AAS can be used to test for metallic elements in rivers, drinking water, in the air, in petrol or drinks, etc.